Welcome to G Fun Facts Online. Let's get straight into the deep end of astrophysics. For billions of years, we believed the cosmos had a playbook. We thought the life and death of stars followed a strict celestial bureaucracy, a set of thermodynamic laws that dictated exactly how massive a star could be, how it burned its fuel, and precisely what it left behind when it died. Physicists spent decades reading the fine print of stellar evolution, and they were confident they knew the limits. But in the last few years, the ground has shaken. Quite literally. It started with a ripple in space-time, a specific frequency, or chirp, heard by our gravitational wave detectors that, according to our best theories, simply should not have existed. It was the sound of two giants colliding. Black holes so massive, they defied the standard models of physics. They were impossible objects, monsters lurking in a mass range that theory said should be absolutely empty. Today we are going to dive deep into the Pair-Instability Mass Gap, the forbidden zone of black hole physics, and discuss the recent, shattering conformations like GW190521 and GW231123 that are forcing us to rewrite the history of the universe. To understand why these recent discoveries are so disturbing to astronomers, we have to start with the standard model of stellar death. This is the story of a war between gravity and pressure that lasts for millions of years. A massive star is essentially a pressure cooker. On one side, you have gravity, which is always trying to crush the star inward toward its center. On the other side, you have nuclear fusion in the core, pushing outward. For most of a star's life, these forces are in a stalemate. The star burns hydrogen into helium, then helium into carbon, and so on, fusing heavier and heavier elements to generate the heat and pressure required to hold gravity at bay. But this game has a strict time limit. Eventually, the star attempts to fuse iron. Iron is the cosmic dead end. It is the ash of the stellar furnace. Fusing iron consumes energy rather than creating it. At that moment, the outward pressure vanishes in an instant. Gravity wins. The core collapses, and the outer layers are blasted into space in a supernova. Now, standard physics tells us that what remains depends entirely on the mass of the core. If the core is between about 1.4 and 2.5 solar masses, it becomes a neutron star, a city-sized ball of unimaginable density. If the core is heavier, typically up to about 50 solar masses, it collapses completely into a singularity, a black hole. But here lies the problem. Theoretical physics predicts a self-destruct mechanism for stars that are too massive. This is where the story gets strange. When a star is incredibly heavy, specifically with a helium core between roughly 64 and 135 solar masses, the temperature inside becomes so extreme that high-energy gamma rays start to behave strangely. These gamma rays are the photons providing the pressure that supports the star against gravity. But at these temperatures, they start interacting with atomic nuclei and spontaneously turning into pairs of electrons and positrons. This is Einstein's E=mc² in action. Pure energy is turning into matter. This conversion is disastrous for the star. Photons provide a lot of pressure support. Electrons and positrons do not. So the pressure support inside the star suddenly drops. The star contracts rapidly, heating up even further. This triggers a runaway thermonuclear explosion so violent that it doesn't just collapse the core, it obliterates it. The star is blown entirely apart. No remnant remains. No neutron star. And crucially, no black hole. This phenomenon is called a Pair-Instability Supernova. It creates a mass gap, a desert in the black hole population distribution between approximately 50 and 135 solar masses. According to standard stellar physics, black holes in this range cannot form from dying stars. If you see a black hole in this range, you are seeing a violation of the law. So you can imagine the shock when the Laser Interferometer Gravitational Wave Observatory, or LIGO, and the Virgo detectors picked up signals from black holes weighing 85, 100, or even 140 solar masses. The scientific community didn't just see a new data point, they saw the impossible. The event that first cracked the dam occurred on May 21, 2019, catalogued as GW190521. The signal was short, a mere tenth of a second, resembling a dull thud rather than the long chirps of lighter mergers. The analysis revealed a nightmare for theorists. The primary black hole was about 85 solar masses. That sits squarely in the forbidden range. The secondary black hole was about 66 solar masses, teasing the edge of the gap. Even more staggering, they merged to form a final remnant of 142 solar masses. This remnant was the first definitive detection of an intermediate mass black hole, the elusive missing link between small stellar black holes and the supermassive monsters at the centers of galaxies. The energy released in those final milliseconds of the merger was equivalent to 8 solar masses converted purely into gravitational waves. For a brief moment, this invisible collision was more powerful than all the light from all the stars in the observable universe combined. If that event had been a fluke, we might have written it off as a measurement error or a freak statistical outlier. But the universe persisted. The detection of GW231123, announced in mid-2025, confirmed that the impossible is actually common. This event involved progenitors of approximately 100 and 140 solar masses, merging to form a colossus of nearly 225 solar masses. Both progenitors were deeply forbidden. The mass gap wasn't empty, it was populated. The question shifted from did this happen to how did this happen? If a single star cannot die to create these black holes, then these black holes must not be the children of stars. They are likely the children of other black holes. We are looking at second-generation mergers. Let's break down the leading theories on how nature is building these monsters. The first scenario takes us to the stellar graveyard known as globular clusters. Imagine a dense beehive of a million stars, ancient, and packed tightly together. In the center of these clusters, gravity is a chaotic puppeteer. Heavier objects sink to the middle, creating a segregation of mass. Here, a process called hierarchical merging can occur. It works like this. First, 2 standard stars collapse into 2 standard black holes, say 30 solar masses each. They merge, creating a 60 solar mass black hole. Usually, the force of a merger gives the new black hole a kick, ejecting it from the cluster. But in the densest clusters with immense gravity, the black hole is trapped. This new 60 solar mass black hole, which is now lurking in the forbidden mass gap, sinks back to the center, finds a new partner, perhaps another 60 solar mass giant, and merges again. We actually have a smoking gun for this scenario, and it has to do with spin. Black holes born directly from stars usually have low spins. However, black holes born from mergers inherit the orbital energy of their parents, spinning them up rapidly to about 0.7 times the speed of light. If we detect high spin in these forbidden giants, it points to a hierarchical origin. Recent data from the 2024 and 2025 observing runs strongly supports this cluster dynamics theory for a significant fraction of these events. But there is another environment even more extreme than a globular cluster. This is the Active Galactic Nucleus, or AGN. This is the disk of superheated gas swirling around a supermassive black hole at a galaxy's center. In this scenario, smaller black holes are trapped in the gas disk like debris in a whirlpool. This is the fast lane of black hole growth. The gas does 2 things. First, it creates friction, known as migration torques, that forces black holes to move closer together rapidly, speeding up the merger rate. Second, and perhaps more importantly, the black holes can gorge themselves on the surrounding gas. This is accretion. A black hole in an AGN disk is like a shark in a feeding frenzy. It can grow past the 50 solar mass limit simply by eating, or it can merge repeatedly with other trapped sharks. Some theories suggest the GW190521 event may have occurred in such a disk, which would explain an associated flash of light detected by the Zwicky Transient Facility, something we wouldn't normally expect from a black hole merger. Of course, there is a minority view that challenges the physics of the supernova itself. Some physicists ask if a star could retain a massive envelope of hydrogen that cushions the explosion, or if strong magnetic fields could allow a 90 solar mass star to collapse directly without blowing apart. Recent papers have tweaked the nuclear reaction rates for carbon and oxygen burning, suggesting the gap might start higher, perhaps at 70 or 80 solar masses. But explaining a 140 solar mass progenitor, as seen in the later detections, with stellar evolution alone remains physically arduous. The hierarchical merger hypothesis remains the heavyweight champion. Why does this matter? Why do we care about a few overweight black holes colliding in the dark? It matters because these events are likely the solution to a cosmological crisis, the origin of supermassive black holes. When we look deep into the universe, we see supermassive black holes, with masses of billions of suns existing when the universe was only a few 100 million years old. This is a problem because there simply wasn't enough time for a standard 10 solar mass black hole to eat enough gas to grow that big that fast. They needed a head start. They needed seeds. The forbidden mergers we are detecting now, these 100 to 200 solar mass objects, are those seeds. They are the intermediate mass black holes. We are finally seeing the mechanism of growth in action. We are watching the Lego bricks of the universe's greatest structures being snapped together. As we move deeper into the late 2020s, the LIGO Virgo Keggler network, soon to be joined by LIGO India, is moving from discovery mode to census mode. We aren't just finding these impossible mergers. We are mapping their demographics. We are learning that the universe is messy. It doesn't strictly follow the simple rules of isolated stellar evolution. It is dynamic, interacting, and violent. The mass gap is not a wall. It is a filter. It stops single stars, but it cannot stop the dynamic hustle of dense clusters and galactic nuclei. For the physics enthusiast listening, let's take a moment to look under the hood of how we actually know the masses of these invisible objects. It comes down to the chirp. When two black holes spiral inward, they emit gravitational waves. The frequency of these waves increases as they get closer. This is the chirp. The frequency tells us the total mass. Heavier systems chirp at lower frequencies. The impossible mergers are so heavy their chirps are incredibly deep, almost too low for current detectors to hear, like a bass note vibrating the floor. The amplitude of the wave tells us the distance, and the shape of the waveform encodes the spin and the orientation. The signal from GW190521 was so short, just 0.1 seconds, because the objects were so massive, they merged almost immediately after entering the detector's sensitive band. They only completed about 2 observable orbits before crashing. This brevity makes analysis difficult, leading to alternative theories like eccentric orbits or boson stars, but the heavy binary conclusion has withstood the most rigorous scrutiny to date. The detection of black holes in the Pair-Instability Mass Gap is one of the most significant astrophysical discoveries of the 21st century. It has forced a marriage between the physics of the very small, dealing with nuclear reactions and particle pair production, and the physics of the very large, dealing with cluster dynamics and general relativity. We now know that black holes are social creatures. They live in swarms, they pair up, they merge, and they grow. The giants we see today are the survivors of a cosmic battle royale, climbing the mass ladder one collision at a time. The impossible is real, and it is watching us from the dark. That wraps up this deep dive into the broken rules of the cosmos. Keep looking up, and stay curious.